Welcome back. I'm Dr. Bettina Heinz, who will teach you more about chemistry. And the topic of this episode is the periodic table of the elements, which we have divided into two parts. So let's begin with part one and see what's on the agenda today. Early observations. People started observing certain regularities when they involved the study of the elements. So the triads were first discovered as families of elements, usually of three. Then we have the law of octaves, which is similar to the musical scale. The periodic law started to get more and more consolidated. And the development of the periodic table is attributed to many people. But Mendeleev of Russia is the one who gets the most credit because he was able also to predict with his setup undiscovered elements due to the periodicity, so people would know what to look for. We will also look at the periodic table itself and see how it is subdivided in the modern version today. The main group or representative elements, the transition elements, the inner transition, what makes them these different groups, what do they have in common with each other, and with a modern viewpoint, the SPDF elements. So atomic theory has produced this information for us. The periodic trends are also important to look at. For instance, ionization, energy values, electron affinity, electronegativity, and atomic and ionic radii. So let's begin. Let's look at the early observations. And we come here to a scientist, a natural philosopher of Germany by the name of Dobereiner, Johann Wolfgang, who started putting elements together that behaved in a similar fashion. And he realized that there was a law of triads. That means he could group the elements according to the then known atomic weights and could anticipate a center element that would be the average of properties from the one above it and the one below it. For instance, we have here calcium, strontium, and barium. The atomic weight for calcium, the value of today that I put here, is 40.08. Barium is 137.34. And when you add those up and divide them by 2, you come very close to the actual atomic weight or atomic mass. Remember, weight is a force and mass is a quantity on its own. So we find about 88. Other groups behave similarly, like the alkali formers, the alkaline metals as we call them today. Lithium and potassium have known numbers, and the middle one can be derived from the other two by averaging out. So 7 plus 39 is 46 divided by 2, and the atomic weight or mass of sodium is 23. You can look it up. And we have here another group of triads, or another triad group, the halogens as we call them today. And they were called in the old days the salt formers. And halogen literally means that in Greek. So we have 35.5 for chlorine, 127 rounded about for iodine, and we add them up, divide by 2, and we get bromine with 80. So you see that was already observed and helped further studies along. John Newlands is another interesting individual here who also studied the known atomic numbers, the atomic weights of the then known elements, and he tried to group them in a certain fashion. But usually they made diagrams. They didn't really make a table like Mendeleev did later. But he noticed something interesting as well. He was an industrial chemist of England, and some people think that Newlands was actually the originator of the periodic table. So he noticed the law of octaves, and he figured out that the 8th element of every group of 8 turns up to have properties similar to the first one. So you go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, etc. So we have a periodicity based on the number 8, actually 7 elements, but the 8th is a repetition of the first. Essentially, not completely, but as far as the properties go. So he likened it to the octave of music, of musical notes like do, re, mi, fa, sol, la, ti, do. And of course, people ridiculed him and thought, oh, this is just stupid and it's a coincidence. So he had a hard time to get established. But he relied on the atomic weights determined very carefully by the Italian scientist named Cannizzaro, who reproduced very reliable atomic weight values. So you needed a good set of atomic weights. They based often their weights on equivalent weights, which is not the same as the atomic weight in the old days. So here we have a picture of Döbereiner, and he was known to be the science teacher of the famous German poet Goethe, who also, besides being a poet, was a scientist. He studied plant morphology, color theory, and many other things. He was the one who noticed the family or genetic behavior of certain elements that turned out to be triads. Now later on, people included other elements, made tetrads and pentaads, etc. So more and more elements joined the group of the triads. Here we have a picture of John Newlands, and his law of octaves is based on Cannizzaro's atomic weights. So Cannizzaro, in about 1860, determined good, reliable atomic weights for about 60 elements that were known in 1860. No coincidence intended. Here we have Newland's periodic table, and you see how he grouped them according to increasing values. And as I already mentioned, people gave him a hard time. Like many scientists who come up with something new, always have a struggle. And based on these new and reliable atomic weights, the German chemistry professor Julius Lothar Meyer, who worked on many other projects as well, he determined that hemoglobin binds to oxygen. So he was also involved in other topics. In those days, people had a wide range of research. He studied also periodicity of elements. Particularly, he related atomic volumes in relation to atomic weight and noticed that there was an interesting repeatability of data. So the top is the modified version of his original, which is here shown below. And this is Lothar Meyer's periodic table. It's more like a diagram. He produced two versions, an early one and a later one. And simultaneously, or a little, let's see, this was 1862. So there was also a very interesting French geologist by the name of Béguier de Champ-Courtois, who noticed also the periodicity, but he grouped the elements in a spiral. And all the elements that are in the vertical column or in a group have similar chemical behavior. So in a way, this method of showing the periodic table also shows very nicely the periodicity. However, since he was a geologist and used geological terms and not so much chemical terms, his paper went pretty much unnoticed, and he didn't include this diagram. So that would have helped. So he was pretty much ignored. Here is a modern periodic table that is based on Mendeleev. This table was very common in textbooks up to the Second World War about. so everything is grouped together. And here we have a picture of Dmitry Ivanovich Mendeleev. He was born in Siberia, and his mother helped him to come to Moscow, and she propelled his career. So he said the properties of the elements are in periodic dependence upon their atomic weights. So a periodic law was now exquisitely or distinctly established, and from then on, things went ahead in a very fast pace. This is, for instance, a periodic table I found in an old physics textbook of 1936. You see how closely related it is to Mendeleev's version. Today we have this atomic table that we show here on the top picture, because it fits better in textbooks, the format, the 8x12 format. And this is the one, as I already mentioned, found in our textbooks, but it should actually look like the bottom one, which is the stretch limousine of the periodic table. Now these bottom, the purple ones, these elements are called the inner transition elements, or the lanthanides and actinides, according to the first transition element that opens up this special row. The lanthanides were often referred to, and are still referred to, as the rare earths, because they are very rare. And uranium is the last actinide, the last full purple circle that we see here, that is found in nature. And that is the one that has a fissionable isotope that led to the discovery of atomic energy. Now we see here, let's look at the top one more carefully, and we see here that we have the main group elements, which are the yellow and the blue. That means they're involved in filling up the outermost shell systematically from 1, 2, and then those are the so-called S elements. And then we continue from 3 to 8, which are the P elements. So those are S and P orbitals that are filled up systematically until the shell is full, which we call the valence shell. Now, except for hydrogen and helium, which make a short period, as we say, because the first shell can have a maximum of 2 electrons according to the Aufbau rule, 2n square, where n is equal to the shell that we're looking at. So we only have 2 electrons possible in the first shell, so the period is pretty fast completed. And then we have the second and third period, which are involved in filling up the outermost shell, which happens to be always the valence shell. And we have the octet rule. That means no more than 8 electrons can be in the valence shell, with 2 exceptions: the first period, of course, and a certain phenomenon that we consider to be octet expansion. So there always are exceptions to the rule, as we see. Then we have the green dots, or the green circles, that represent the transition elements. The transition elements are those that are not involved in filling up the outermost shell anymore. They are involved in cleaning up unfinished business and bringing up the second to the last shell with filling up of the d orbitals from 10 to, from 8 to 10. So we have here, remember the fourth shell and the third shell can have 2n square. So 3 square is 9 times 2 is 18. So they're building up the shell from 8 to 18. So 10 elements are involved here. So every time we have here 10 elements. And then we come further down where we go into the higher shells. And the fourth shell, 4 times 4 is 16, times 2 is 32. So the fourth shell can have a maximum of 32. But you know, you can't fill them up once they're the outermost shell to the proper number, because we have the octet rule to consider. So nature does it in such a way, it builds up the outermost shell or starts a new shell with 1 or 2 electrons and then goes back down and completes those shells that need to be completed. Like from A to 18 are the transition metals, and then we have from 18 to 32, which involves 14 elements that are called the inner transition elements, the lanthanides and actinides. Here we also see some circles that have X's in them. Those are all artificial elements, man-made, produced by bombardment experiments. I would call that particle billiard. So you target atoms with fundamental particles and try to get heavier and heavier atoms. And usually they have a very short lifetime. They cannot even be held in your hand. There's no real tangible material there. But with a spectral peak in a mass spectrogram, they can say, aha, I just discovered a new element with a mass number such and such. So that is often enough to complete the periodic table. But nature has a limit, and the limit is stability of the nucleus, because later on the elements get more and more radioactive. They want to throw off excess baggage like a camel train in the desert. So here we have the circles with an X. That means nowadays they have real names, and the open circles are still unknowns. That means they are discovered, but they don't have any names yet. And we have here, most of the actinides are all man-made. Here we have the long version of the periodic table, which shows you that we move from the top left to the top right and go meandering through the rows. And you can already imagine that if we would have theoretically more elements, the periodic table would get broader and broader and broader, because we would have more and more transition elements that need to fill up the numbers in the required shell particle amounts. We are stopping here with 32, but it can go all the way up to 50 and more. But that's just a mathematical concept right now for us. But nature has a limit. So I like this periodic table. So if you want to go back to the original one, all you do is cut out these inner transition elements, the so-called F group elements, and put them below and move the other columns together. By the way, the groups, the vertical groups of elements are called groups, and the horizontal groups are called periods. So the periodic table is divided into groups and periods. Now we notice periodic trends. So let's look at some periodic trends here. Here we have the short version of the periodic table. And one of the most interesting concepts or phenomena is ionization potential or ionization energy. That means how much energy do I need to knock off one electron from the valence shell of an element. So that is more or less difficult. Now sodium is very easy to ionize, because when sodium loses its outer electron, the lower shell surfaces and becomes the so-called valence shell, and that is very close to the noble gas shells. So sodium will then have the electron configuration of the next noble gas, which is neon. Chlorine, however, does not want to give up any electrons, because it just needs to accept an electron to get a good stable octet. So that's very difficult. So we have here a trend. The ionization energy increases from left to right, because you have to use more stress on the element to give up its electrons. They only do it under the gun, so to speak, on the right top corner of the periodic table. So the trend is a decline from top to bottom within a group. So it decreases within a group, but increases from left to right. Let's look at another interesting phenomenon, which is electron affinity. It's sort of almost similar. It's just the reverse in the sense of the ionization energy. How much energy is released when we force an electron onto an atom? Will it take that electron greedily, or will it say, no, I don't need it, get out of my sight? So in one way it's very easy, in one way it's very difficult. And these values are also tabulated, and we see here the same trend as the ionization energy. The electron affinity increases left to right and drops top to bottom. And another interesting phenomenon that is derived from those two that I just discussed with you is electronegativity. This cannot be measured directly, but with the help of electron affinity and ionization energy divided by 2, we get what we call the electronegativity. And this can only be discussed in the concept of a chemical bond. So the larger the electronegativity differences are of the elements combining, the more we have an electron transfer type of bond to expect, which we call ionic bonding. So a rough guideline is maybe the difference in En, or electronegativity, 1.5. And if it's lower than that value, then we have what we call covalent bonding, where the elements share the electrons and produce electron pair bonds, which we call molecular type of bonds as well. And of course, the electronegativity, if it's a little different, then 0 when you subtract the two from each other. Then we have a polar molecule. That means whatever atom has a high electronegativity has the bulk of the electron density, and we can determine that with the electron distribution, which is not fairly distributed between the partners, and also with a vector, polarity vector that is shown, and also with delta plus and delta minus, which means differential of a charge. Here we see a table of the first ionization energies, and we see some irregularities here, but later on people found out that that has to do with temporary filled sub-energy levels. So full energy levels always mean an increase in stability. Here we also have a trend of atomic radii, and here we show that within the groups, the atomic radii, that means the size of the atom, increases. Why? That's easily explained because we have more and more shells. So the group elements have the same number of valence electrons, but different number of shells. And the outermost electron is pretty far away from the nucleus, because the nucleus is shielded by the inner shells, so that if we only have one electron, then it can migrate pretty far away from the nucleus, and that's what makes the atoms pretty big. We have the Coulomb's law of attraction, charge 1 times charge 2 divided by the square of the radius between them. Okay, and here we have, since the valence electrons increase from left to right, the Coulomb's law, or the attractive power, is much higher now to the nuclear positive charges. So they have a bigger number of charge quantity in the valence shell, so that makes the attraction power stronger, and we have a shrinkage thus in the atomic size. But still we have the same trend in the columns. So we can say increase right to left and increase top to bottom. Here we have the comparison of the ionic radii with the atomic radii. Now interesting, when we go from electropositive elements, that means those elements that have a low electronegativity, and they lose their outer electron, they shrink all of a sudden because they've lost a whole outer shell. So you can see that the ionic radius is much smaller than the atomic radius for the positive ions. On the other side, the negative ions, since they pick up an electron, the electron acceptors, so that extra electron increases the repulsion of the electrons in the valence shell, so they want to have a bigger distance from each other, and that leads to an inflation or an inflated volume of the ion. And I'd like to point out to you some of the sizes of these ions. Look at the tellurium ion, the telluride. It has a radius of around about 0.2 nanometers. That means the whole diameter would be 0.4 nanometers. Remember, a nanometer is 10 to the 9th meter. And also the nitride ion is pretty big. So you can see that when we look here at the main group elements, we can see some distinct differences. However, the transition elements and the inner transition elements are not, they're not worthy of being listed here so much because the trend is not as obvious as with the main group elements. So you see there is some distinction. The positive ions shrink, the negative ions fatten up, and there's a group missing in the fourth group. Now what's their problem? Well, they do not make ions. They are mainly involved in covalent bonding. So let's look at the periodic table here once more, and I will review what we've learned. We have here our short version, and remember the groups across, or the horizontal list of elements, represents a group that we call the periods. The columns that are in vertical position are called the groups. Now what do the groups have in common? The groups fill up the same shell with electrons. I'm sorry, the valence shell has the same number of electrons, but they have different number of shells. The periods are the ones that fill up the same shell with consecutive electrons. So they have the same number of shells, but different number of electrons. Let's look at some important groups here. We have the main group elements, as you remember, and they sometimes have their own names. Like group 1 are the alkaline, group 2 the earth alkaline, group 7 are the halogens, and group 8 are the noble gases. And the noble gases have a complete valence shell, so they're very, very stable. And I would like now to conclude this episode and see you next time.